titled Fluid Mechanics Revision Sheet. I'm assuming you would have attempted problems from the sheet by this time and ready to take it head on. So the first problem of the sheet is about a floating mass at the interface. There is this liquid of density twice sigma and there is a mass which is a cube of side A and made of material of density sigma, just about floating, cube of side A, made of material of density sigma. The weight is supported by two springs. There is no upthrust because there is no part of the mass which is inside the fluid, right? And it's given that each of these springs is equally deformed, which means if this is compressed, if this is elongated, this must be compressed, right? This must be elongated so that this exerts an upward force. This must be compressed so that this exerts an upward force. Yes or no? So this elongated and this one compressed. So this exerts an upward force kx. Because of elongation, because of compression, this will exert an upward force kx. Together, this supports the weight. Together, this supports the weight. That means 2kx must be equal to the weight of the body, right? Now, the next that is done is a weight is placed on the block so that it is half immersed in the liquid, right? So now, this is the interface of the liquid. And half immersed. This gets additionally compressed by A by 2. The upper one gets additionally elongated by A by 2. Yes or no? So the spring force, the new spring force here is kx plus A by 2. X minus A by 2. So plus A by 2. And the force here is going to be yes or no? In this case it's going to be x minus A by 2. Extent of compression, isn't it? X is the elongation. That is how it is. Right. So the force will increase. In this case the elongation was x units. Now the elongation has increased by A by 2. Yes or no? Right? All that you need to now do is, you need to, and say a weight W naught is placed here. A weight W naught is placed here. Clear? Now if a weight W naught is placed here, the new spring force will support the upthrust plus the weight, total weight. Right? So what's the new spring force? Kx plus A by 2 plus Kx plus A by 2. Isn't it? Right? That's the upward spring force. Plus the upthrust. What's the upthrust? This is in a fluid of density 2 sigma. Right? So 2 sigma into A cube by 2 into G. That's the upthrust. And what it must do is, it must support W plus W naught. W plus the weight W naught. And what you could do here is 2kx. 2kx you can replace by W. So this W will get cancelled with 2kx. And you can obtain the value of W naught. Yes or no? Do you realize that? W naught could be obtained from this because kx plus kx, 2kx will get cancelled with W here, and W naught can be obtained. Sounds good? Does it make sense? Let's move on to the next problem. Problem 2. So, outside the mercury surface in the tank, the closed tube length is L. There is a tube and there is length L. There is length L. Okay. Length L. This way. The tube when immersed in mercury, the mercury rises by L by 4. So, when immersed in mercury, mercury rises by L by 4. When immersed in mercury, this is now mercury. Mercury rises by L by 4. While atmospheric pressure is 3L by 4. That means the pressure here is 3L by 4. Is 3L by 4. Which means now there is air in this, right? There is air in this. Clear? This air must exert a pressure such that the total pressure here is 3L by 4. So if this exerts a pressure P1, then very clearly P1 units in terms of length of mercury column, P1 in terms of length of mercury column plus L by 4, which is this length of mercury column, must give me 3L by 4. Yes or no? Right? So the pressure in length of mercury column is L by 2 for this air column, yes or no? Now, so what is done is it's immersed in a liquid, in another liquid. There is no vacuum at the top, and now it's immersed, the same situation, it's immersed in another liquid. The pressure inside the tube becomes 2L by 3. That means now, when the whole thing is immersed in some other liquid, the pressure inside the tube, that means the pressure here, P2 becomes 2L by 3. What is the length of the air column now? Say X units of air column. Now, essentially, you know, this length is 3L by 4. Right? This length is 3L by 4. See, the air column, the molecules of air in both situations must have been the same number of moles of air. It's just compressed by different amounts, right? In both situations, the quantum of air in the tube must have been the same. Originally, there was a length L of air, which got compressed to a length 3L by 4. Now, when taken out, it's the same amount of air. When immersed in this liquid, it got compressed such that the new length of air column becomes X. So we have the same number of moles in both this, and we will assume that the whole thing took place under isothermal conditions. That means we could apply Boyle's law to the situation. Boyle's law to this situation. Now, the pressure initially is L by 2, volume is proportional to the length, right? So can I say P1 V1 must be equal to P2 V2, applying Boyle's law to the air column in both situations. P1 V1 is P2 V2, so P1, which is L by 2, into V1, which is the length 3L by 4, is P2, which is 2L by 3, into the length X. Yes or no? So that makes it 9L by 16. 9L by 16 is the new length of the air column when you immerse it in some other liquid. Got me? How many of you were able to solve this independently? No. No one. But you understand this now? See, essentially, you know, the whole thing was just an air column of length L. The whole thing was an air column of length L. And the air column of length L, this was at atmospheric pressure initially, right? And the same number of moles appeared here and same number of moles appeared there. That is the whole idea, which means you can compare this and apply Boyle's law. Sounds all right? So in the next problem, there is a trolley there is this trolley filled with a liquid and moves on a smooth incline, making an angle alpha with the horizontal. Now, when it, and assume there is no friction, assume the inclined plane is fixed. So when it moves down initially, what is its acceleration? G sine alpha. Its acceleration is going to be G sine alpha. That would be its acceleration. Now suddenly, the acceleration of the trolley becomes 2g sine alpha. By some mechanism, the acceleration of the trolley becomes 2g sine alpha. Right? We now want to find the inclination theta of the free surface of the liquid with the horizontal. Inclination theta of the free surface with the, this is the free surface of the liquid. We want to find its inclination with the horizontal. That's the problem in hand. Clear? Okay, now do you remember the following? First of all, I'm not sure if you do, but so if there is a trolley moving on a horizontal surface, and if this is the free surface, initially horizontal, if it moves with constant velocity, this will be horizontal. If it's given an acceleration ax to the right, then it becomes inclined like this, then tan theta would be ax by g. Right? Remember this? Now, if in addition it's given a vertical acceleration ay, then effective g becomes g minus a. However, if it is given a vertical acceleration ay, g, and a horizontal ax, then the theta, revised theta would be ax, effective g would be now g plus ay. Right? Do you remember all of this? That's the idea that we are going to deploy for this problem. Now, this is 2g sine alpha. This angle is alpha. It has a horizon, this angle will be alpha, therefore. This would be 2g sine alpha cos alpha. Horizontal acceleration ax, right? That will be its horizontal acceleration. Its vertical acceleration would be ay, where ay is 2g sine alpha sine alpha, right? That's a vertical acceleration. So then, if I know ax and ay, I can find tan theta equal to ax, which is 2g sine alpha cos alpha divided by g minus ay. Yes or no? Which is g sine 2 alpha divided by g into 1 minus 2 sine square alpha is cos 2 alpha. That makes it tan 2 alpha. That's tan theta. So therefore theta must be 2 alpha. Theta therefore must be 2 alpha. Right? Were you able to solve this problem? Yes? Okay. Let's look at the next one. There is a tank that rests on a smooth horizontal table. This is a tank. It rests on a smooth horizontal table. And has two identical holes on either side of the tank containing a liquid. So, say there is a hole at a depth h1 from the free surface, and say there is another hole at a depth h2 from the free surface. It does not matter. We want to find the force required to keep it in equilibrium. Say if rho is the density of the fluid, then do you realize that V2 in this case would be root 2gh2? The velocity of efflux in this case, V1, would be root 2gh1. Now, this will exert a reaction force rho a V2 squared like this, right? When this is again a standard result, rho a V2 squared is the reaction force. A is the area of cross section of this tube. We'll assume that this also has the same area of cross section, right? Rho a V squared. And this, when it spurts out, it will exert a reaction force which is rho a V1 squared in the opposite direction. So then, what is the net force acting leftwards? The net force acting leftwards is rho a V2 squared minus V1 squared. And this must be compensated by a rightward force F to keep it in equilibrium. Yes or no? Right? So which is like rho a V2 squared minus V1 squared is 2g into H2 minus H1. But H2 minus H1 remains constant. H2 minus H1, the difference between the depths of these two nozzles will remain the same. So this is a constant. So force remains constant. The height of the upper hole from the surface is h, and F is the horizontal force required to keep the tank in equilibrium. So force versus h. No. So the height of the upper hole will change, h1 will change. So this is h, say. This is h. So height of the upper hole will change, but h2 minus h will not change, isn't it? Huh? They're not at the same depth. See, if they were at the same depth, then anyways f will be 0. Then also it will be constant. Then also it will be constant, isn't it? Then rho a v squared on either side would cancel off. Huh? How can H2 minus H change? That's the difference between the depths of these two holes. How can H2 minus H change? Because H2 will also change. If H changes, H2 will also change, isn't it? H2 minus H is the difference in the depths. How will that change? Huh? Sorry? How can H2 be constant if water is flowing down? If this level is going down, how can H2 be constant? If this level is going down, how can H2 or H either way be constant? The difference is constant. The difference, this depth will go down, this level will go down, but H2 minus H will remain the same at all times. Yes or no? Right? So this will be a constant number. This will be a constant number because H2 minus H is constant. So force versus H is a constant. So option D. Clear? So two layers of liquid, one of density rho, another of density 2 rho, and there is a point A which is at a depth h below the free surface, and there is a point B which is at a depth h below the interface of the two liquids. The first one is 2h units, the other one is this lower fluid, right? We want to find PA minus PB. Now that's a very simple problem because what is PA? PA would be atmospheric pressure plus rho GH. That's PA, right? What is PB going to be? P naught plus rho G2H plus 2 rho GH. Yes or no? Which is like P naught plus 4 rho GH. So the difference in pressures, PB minus PA, is going to be 3 rho GH. Let's look at the next problem, problem 6. So here we have a pulley system with a mass A here, mass B there in a container, mass of B is given to be 3m, the density of the block B, rho of block B is given to be 2 rho, that's the density of this. The density of the liquid is rho. Liquid is rho. The system is released from rest. The system is released from rest so that the block B moves up with when in liquid and moves down when out of liquid with the same acceleration. We want to find the mass of block A in terms of m. Okay. See, in this state, it is said that this moves up with an acceleration, right? It moves up with an acceleration A. And when out of the liquid, it moves down with an acceleration A. It moves down with an acceleration A, right? We want to be able to find mass of A in terms of m. That is what we want to find. Okay. When out of the liquid, very clearly, do you realize that A would be mb, which is 3m minus ma into g by 3m plus ma. Do you understand why? You could always imagine this system to be opened up like this. So, yeah, so you imagine the system to be opened like this, BA, where there is going to be, as if there is 3mg acting this way and mag acting this way. Tension will be an internal force. Net force would be 3m minus ma into g divided by ma plus mb. You could always open up a pulley system, masses this way, and compute the acceleration without writing two equations for two masses. Do you all understand this? Huh? This is like 3 mbg, this is like mbg minus mag by ma plus mb. That's a rightward acceleration, which in effect is the downward acceleration of B and upward acceleration of A. Now, in this case, see, there is mag acting downwards, mbg acting downwards, and there is an upthrust acting on it upwards. Yes or no? Upthrust will be equal to weight of liquid displaced. Yes or no? So, what is the upthrust equal to in? Upthrust on B. What is the volume of liquid that it displaces? It displaces 3m by density of the liquid. It displaces its own volume. It displaces its own volume. Its own volume is by 2 rho. This is the volume that it displaces. This is the volume that it displaces, isn't it? It displaces its own volume. 3m by 2 rho is its own volume. Now the mass of the liquid of this volume would be into rho into g. That's the weight of the liquid that it displaces. And this must be the upthrust, right? So which is like 3m by 2g by 2g. Yes or no? The entire. Yes, yes. It displaces its own volume, no? Now, for this situation, it's ma minus, so acceleration upwards is ma minus 3m into g plus upthrust, which is 3mg by 2 divided by 3m plus ma. Do you all understand what I did here? I can explain again. I'll explain. See, just open it up. So mag, 3mg acting this way and upthrust acting leftwards. Right? If you just imagine it to be opened up this way. Clear? And all that you need to do is equate this acceleration to this acceleration. So this acceleration is going to be 3m minus ma into g divided by 3m plus ma. And you can solve for ma from these considerations. Yes or no? Sounds all right? Water from a tap emerges vertically downwards with an initial velocity v naught. Velocity v naught. Assume pressure is constant throughout the stream of flow and the flow is steady, find the distance from the tap at which the cross section is half the cross sectional area of the stream at the tap. So absolutely, this is the original area A, and we want the area to become A by 2. The velocity is V naught here. The velocity here is going to be root V naught squared plus 2gh. H is the height that it falls, isn't it? Isn't it? And now apply continuity considerations. So V naught into A, volume flow rate here must be equal to volume flow rate there. A by 2. This is all that you need to do. The volume flow rate at this cross section must be the same as volume flow rate at this cross section. Yeah, so V naught squared plus 2gh is 2V naught. That it is. Make sense to all of you? Okay. So this is floating. Weight of the combined mass must be equal to the weight of liquid displaced, right? So, or also mass of this combined mass must be equal to the mass of the liquid displaced, Now in this state, what is the contribution of the liquid displaced by B? Contribution. So B displaces a mass of the liquid equal to its own mass. Yes or no? Ma plus Mb is the total mass of the body, and that must be equal to the mass of the liquid displaced. That's laws of flotation, because that will be equal to the upthrust. Mass of the liquid displaced would be equal to upthrust, let's say in kilograms, isn't it? So Ma plus Mb is the mass of the liquid displaced by this combo. What is the contribution made by B? Mb. B displaces a mass Mb of the liquid, right? So what is the volume of the liquid that it displaces? The volume of the liquid that it displaces is, it displaces a mass Mb of the liquid divided by the density of the liquid. Yes or no? That's the volume of the liquid displaced in the state. That's the volume of the liquid displaced in the state by Mb alone. Now, when you detach B and chuck it into the liquid, then it will displace its own volume. Yes or no? Then it will displace its own volume, right? So in the new state, when you take it away and plunge it in the liquid, it will displace its own volume. So now what is the volume of liquid that it displaces? Mb by rho B, its own volume. Now, it's given that the height increases, right? It's given that the height increases. If the height increases, means what? It is displacing more volume. It's displacing more volume, isn't it? This height will increase if you displace more volume, right? That means this must be more than this. In order that h increases, the contribution of displacement made by B in the second case must be more than the contribution made by B in the first case of the volume of the liquid displaced. So V prime L must be more than VL. Yes or no? Right? So V prime L must be more than VL. Why? Because H increases. More volume is displaced. That's when H will increase, isn't it? This is the volume displaced in this case by B. This is the volume displaced by B in this case, first case. And this must be more than this, which means MB by rho B must be more than MB by rho L. So which means rho L must be more than rho B. How? Okay, think of it like this, yaar. There is an upthrust, and in order that this be in equilibrium, should it not balance both the weight of A and B? Not just the weight of the portion immersed. It has to balance the total weight A and B, right? Hmm? Hmm? Yes, yes, yes. In the second case, the mass of the liquid displaced by A will remain the same. So that has not changed. That has not changed. Mass of the liquid displaced by A in the second case has not changed. Therefore, A has displaced the same volume of the liquid. Has not displaced the same volume of the liquid. It will change because L will change because now there is less amount of B. But the contribution to the liquid displaced by B alone in both cases will differ. A will still displace a mass Ma of the liquid in both cases. So it will displace the same volume of the liquid in both cases. Yes or no? Hmm? Yeah, which will happen because again new laws of flotation will apply to A, isn't it? Very true. L has to decrease. L has to decrease because there is lesser requirement of an upthrust. Because upthrust now only has to support the weight of A. So there has to be lesser volume of liquid that has to be displaced. In order that there is lesser amount of upthrust to support lesser weight. Now there is only weight of A that has to be supported by upthrust. So there isn't requirement of the same amount of L of the liquid to be displaced. Isn't it? No, no, you're right. I mean, we will assume that, we are somehow immersing it in the liquid. Assume that it is somehow being immersed in the liquid. Yes. I agree with you. You saying I'm not leaving it free. I'm immersing it in the liquid. That is an assumption that we have to make. Okay. See, again, do you remember? If this liquid column is given a velocity like this, then this surface assumes a parabolic shape, right? This will assume a parabolic shape if it's given an angular velocity omega. And if it's given an acceleration A rightwards, it'll become inclined to the horizontal, right? Now if you combine this effect with this effect, all that will happen is that this will shift to the right. All that will happen is that this will shift, combine this with this. Omega with acceleration A to the right. Then all that will happen is the axis of rotation will shift to the right. This would be the net effect. Superimpose the two, this will be the net effect. So that makes, so obviously then L1 has to be more than L2. if it's given an acceleration L to the right, then L1 has to be more than L2 if it's given an acceleration A to the right. Clear? A block of wood of specific gravity 0.6 is submerged in water to a depth of 3 meters in a vessel. So this is a vessel, and there is a block. For calculations, imagine it to be a point mass submerged to a depth h of 3 meters in a vessel. The specific gravity of this is 0.6. Water, of course, rho is 1. The block reaches the surface of water in 0.9 seconds. The block reaches the surface in 0.9 seconds. While the vessel is accelerating up with an acceleration A, we want to find the acceleration of the vessel. We want to be able to find the acceleration of the vessel. See, essentially, I can imagine this to be fixed if I replace G by G plus A. Everywhere, if I replace G by G plus A, I can assume this to be not accelerated and do all my calculations accordingly. You know what I'm saying? Now, if I replace G by G plus A, that means it's the frame of reference is attached to the vessel itself. Right? Now, if M is the mass of the wooden piece, what's the volume of the wooden piece? M by rho. This is the volume of the liquid that it is displacing. This is the volume of the liquid that it is displacing into 1, which is the density of the liquid, into G plus A. Into G plus A is the upthrust. Weight of the liquid that it displaces is going to be this much, which would be upthrust. It's displacing its own volume, rho by 0.6, so rho is 0.6. The volume into density, which is the mass of water, into G plus A, which is the weight of the water that it displaces. And this must be the upthrust, minus its own weight, which is M into G plus A once again. Is the downward force, its own weight, now to be looked upon not as mg but as M into G plus A. This is the net upward force acting. This is the net upward force acting on the mass divided by the mass. That will give me the upward acceleration in a frame of reference. Let's say upward acceleration A naught of this in a frame of reference attached to the vessel. In a frame of reference attached to the vessel. So this would give me acceleration of the block in a frame of reference attached to the vessel. So 5 by 3. So this becomes 2/3 G plus A. 10 by 6. So 5 by 3 minus 1. So that makes it 2/3 G plus A. Right? Now, with this acceleration, it takes 0.9 seconds starting from rest to cover an upward displacement of 3 meters. Right? So h is half gt squared I can apply. H is half at squared, upward acceleration A naught. Right? H, which is 3, is half of A naught. A naught is 2/3 G plus A into T squared, which is 0.9 squared. Can I say all of this? G is 10, and you can easily solve for A, the acceleration of the vessel. So we have a U tube this is a liquid of density rho naught. This is also rho naught, height h. So there is a liquid of density rho in the U tube, right? And in both limbs there is liquid of density rho naught poured, right? One a column of length h by 3 of rho naught, another one a column of length h of density rho naught. So that this is the state. So that this is the state of equilibrium. Clear? So yes. So now I want to find the value of rho by rho naught, for which this could have been obtained very clearly. Equating pressure at this level. What's the pressure here? See, atmospheric pressure is the same on both sides, so I can forget all about the atmosphere. So I'll just look at the pressure because of the liquid columns. So rho naught GH must be equal to rho naught G h by 3 plus this length is h, right? Liquid of density rho. Pressure here is rho naught GH. The pressure here must be rho naught GH by 3 plus rho GH. So rho by rho naught easily obtained from these considerations. Problem number 12. There is a vessel here. This is the free surface of the liquid, and it has a column of length 10 meters. Now there is an orifice here. There is a small orifice here, and at a depth h from this orifice, at a depth h above the base, this orifice is located. That means this is 10 minus h. At a depth 10 minus h meters below the free surface, there is this orifice from which liquid spurts out. Now there is this inclined plane. This angle is 30 degrees. The stream that comes out from this hole, let's say with a velocity v very clearly would be root 2g 10 minus h, right? The velocity of a flux here. The stream that comes out of here hits the plane normally. That means the parallel component, this is perpendicular, the parallel component of the velocity becomes 0. We want to be able to find h. We want to be able to find h. You know what I'm saying? Repeat. You want me to repeat? No, at this instant, the stream that comes out at this instant hits the plane normally, right? Now, again, what we'll do is we'll resolve velocity parallel to the plane and perpendicular to the plane. This is the direction of the plane and it makes an angle 30 degrees with the horizontal. So the initial velocity parallel to the plane is v cos 30 degrees. v root 3 by 2. The initial velocity perpendicular to the plane is v sine 30 degrees, means v by 2. These are initial velocities parallel and perpendicular to the plane, right? Now if you look at g at all times is g downwards, right? This is 30 degrees. G cos 30 degrees, which is g root 3 by 2, is the component of acceleration perpendicular to the plane, right? And g sine 30 degrees, which is g by 2, is the retarding acceleration parallel to the plane. Yes or no? G sine 30 degrees. How about it? Now, suppose it takes t seconds to go from A to B. Suppose it takes t seconds to go from A to B. That means in t seconds, the parallel component must have become 0. So, in the parallel direction, I can apply v equal to u plus at. In the parallel direction, I can apply v equal to u plus at, where a is minus g by 2 in the parallel direction. A is minus g by 2 in the parallel direction, and final v becomes 0 in the parallel direction. So, can I say 0 final velocity is initial velocity in the parallel direction, which is v root 3 by 2 minus a is minus g by 2, as you can see, minus g by 2 into t. That's the time it takes to hit the plane. So, t then must be v root 3 by g. T then must be v root 3 by t by 2, right? That's the time it takes to hit the plane. Now, in this time, it falls a distance y. It falls a distance y, where y is half gt squared. Y is half gt squared. Right? It only has a horizontal velocity. So, displacement in the vertical direction in t seconds. Acceleration in the vertical direction is g. So, half gt squared is the height fallen in t seconds. Initial velocity in the vertical direction is 0. So, y equal to ut plus half gt squared. U is 0 in the vertical direction initially. Yes or no? Also, the horizontal length that it covers in t seconds would be v into t. V into t would be the length L. Yes or no? Because this velocity, horizontal velocity, remains constant because acceleration is vertical, right? So, v into t is this length L? Yes or no? So, the length L is v into t. V into t means v squared root 3 by g. What is this? 30 degrees. What is this? This length is h, so this will be h minus y. Yes or no? So, can I say tan 30 degrees is h minus y by L? Tan 30 degrees is h minus y by L? Or tan 30 degrees is 1 by root 3 is h minus y. Y is half g into t square. Three by 4 into v squared, right? Half g v squared by 4. Huh? By g, sorry, g. Right, v root 3 by g. I'm sorry, this, right? Is that all right? See, y is half g t squared. T is v root 3 by g, right? So, this y is essentially 3v squared by 2g. 3v squared by 2g is this y, right? So, tan 30 degrees is 1 by root 3 h minus y, which is 3v squared by 2g, divided by L, which is v square root 3 by g. Yes or no? Where v squared by g, again as you can see, v squared is 2g into 10 minus h. So replace this v squared by 2g into 10 minus h, right? So 1 by root 3 will get cancelled. So 1 v squared by g, v squared is 2g into 10 minus g, 10 minus h, sorry, by g is h minus 3 by 2g, 2g into 10 minus h. Yes or no? G will get cancelled, 2g will get cancelled, and you can solve for h from this equation. You can solve for h from this equation. What does it turn out to be? Huh? 8. 6h is 40. 20 plus 30. 20 plus 30. 50. 50. H is 8.33. 6h is 50. H is 8.33. Clear? Passage, problem number 13. There is a ball of density D, and let's say its volume is V, is dropped onto a horizontal solid surface. It bounces elastically from the surface and returns to its original position in time t1. That means this time is t1 seconds, right? That means the time it takes to come down is t1 by 2, right? Yes or no? That means the velocity with which it hits the surface is gt1 by 2. Now it's released and it falls through the same height, from the same point it's released. And it falls through the same height before striking the surface of a liquid of density dl. Obviously it will strike with the same velocity gt1 by 2 is the velocity with which it strikes. Find the time which the ball takes to come back to the same point P. That's what we need to find. If D is less than DL. If D is less than DL, obviously upthrust will be more than the weight. Upthrust will be more than the weight, and while it goes down, it will get retarded. It will get retarded. Its velocity will become 0 at some point A. Its velocity will become 0. Now, when inside, its retardation, magnitude of retardation is upthrust minus weight. Upthrust is what? Weight of the liquid displaced. Weight of the liquid displaced, mass of the liquid displaced is V into dl minus its own weight. That's the upthrust. That's the upthrust divided by its own mass, which is V into d. That's the retardation. This is the net upward force divided by its own mass. That will be the net upward acceleration, which is the retardation, which is dl minus d by d into g. So the time, and it strikes with a velocity v. So the time it takes, say t2 seconds, t2 seconds that it takes for its velocity to become 0 under this retardation, given that it starts with a velocity v, t2 then would be v by a. Yes or no? That's going to be t2. V by a means gt1 by 2 this. That's the time t2 it takes to reach this point A where its velocity becomes 0. Then it starts with 0 velocity. Do you realize and its acceleration remains the same upwards? So it's same as gravity. It will take t2 seconds to reach this point. And then, so it reaches this point again with a velocity gt1 by 2. And it will take t1 by 2 seconds to go up. So the total time it takes is t1 for this plus 2t2. t1 plus 2t2 is the total time it takes to come back to the point P. So the total time taken is t1 and 2t2. Minus t. Yes or no? Which is t1 into dl by dl minus d. Right? That's the time it takes. T into dl by dl minus d is the total time it takes to come back to the point P. Right?